Maneuvering into lunar orbit, detailed breakdown of Resilience's $5 million navigation system. The Resilience lunar mission, which spans from Q1 2023 to Q4 2024, represents a significant leap in space exploration technology with a dedicated navigation system budgeted at $5 million. This system is meticulously designed to facilitate precise trajectory adjustments and thruster calibrations, ensuring a successful insertion into lunar orbit. The mission is structured around 5 critical phases, each essential for the navigation and operational efficacy of the spacecraft. Key phases of the navigation system. 1. Phase 1, Initial Trajectory Setup, Q1 2023. The Resilience mission commenced with the initial trajectory setup in the first quarter of 2023. During this phase, mission control teams utilized real-time data from various ground stations to establish the spacecraft's initial flight path. This process involved extensive calculations to determine the optimal trajectory for reaching the Moon. Moreover, the phase required establishing robust communication links between the spacecraft and ground control, ensuring reliable data transmission. Calibration of onboard instruments was also a significant focus, as it laid the groundwork for accurate navigation throughout the mission. 2. Phase 2, Mid-Course Corrections, Q2 2023. As the spacecraft journeyed away from Earth, the mission entered the mid-course correction phase in Q2 2023. This stage featured a series of trajectory refinements where adjustments were made to account for gravitational influences from celestial bodies and potential perturbations due to solar radiation pressure. Sophisticated algorithms processed real-time telemetry to calculate necessary trajectory corrections, ensuring that the spacecraft remained on its intended path toward the Moon. The successful execution of these corrections was vital for maintaining the spacecraft's momentum and direction. 3. Phase 3, Lunar Approach Preparation, Q1 2024. Entering Q1 2024, the focus shifted to preparing the spacecraft for its final approach to the Moon. This phase involved intricate simulations and rigorous testing of the navigation system to validate its performance under conditions expected during the lunar approach. Engineers conducted various drills to ascertain that all systems were operational, including thruster functionality and sensor accuracy. The goal was to ensure that the spacecraft could perform the complex maneuvers required as it neared the lunar surface, particularly in the context of gravitational interactions and orbital dynamics. 4. Phase 4, Lunar Orbit Insertion, mid-Q2 2024. The most critical phase of the mission occurred in mid-Q2 2024 during the Lunar Orbit Insertion maneuver. This stage required precise thruster firings to slow the spacecraft sufficiently to be captured by the Moon's gravitational pull, allowing it to enter a stable orbit. Engineers meticulously calculated the timing and intensity of the thruster burns, as even minor discrepancies could lead to mission failure. The successful execution of this maneuver was crucial, as it determined the spacecraft's ability to maintain a sustainable orbit for subsequent operations and research activities. 5. Phase 5, Calibration and Operational Testing, Q3-Q4 2024. Following the successful insertion into lunar orbit, the final phase of the mission involved extensive calibration and operational testing of the navigation system. This phase spanned the latter half of 2024, during which engineers conducted thorough evaluations of all onboard systems, including sensors and thrusters. The goal was to ensure that the navigation system operated flawlessly within the unique lunar environment characterized by lower gravity and varying thermal conditions. The successful completion of these tests was essential for transitioning the spacecraft from the insertion phase to its operational phase, where it would conduct scientific research and exploration tasks. Common key points across sources. Across various sources discussing the Resilience mission, several key points consistently emerged. The critical importance of precision navigation for lunar missions was emphasized, highlighting the advanced technology required to ensure mission success. The phased approach to trajectory adjustments was recognized as a vital strategy for managing the complexities inherent in lunar navigation, with each phase building upon the success of the last. The significant investment in the navigation system was viewed as a pivotal factor in the overall success of the mission, underscoring the commitment to leveraging cutting-edge technology in space exploration. Differences between sources. While there was a consensus on several aspects of the mission, some differences among sources were noted. Certain sources focused on the technical specifications of the navigation system itself, detailing the hardware and software employed, while others highlighted the strategic partnerships and collaborative efforts that supported the mission's development. Variations in the timeline details were present, with some sources providing more granular insights into specific testing phases or the technologies utilized in the navigation system. Complete timeline of events. Q1 2023, initial trajectory setup and system calibration, focusing on establishing communication and precise navigation parameters. Q2 2023, execution of mid-course corrections to refine the trajectory as the spacecraft moves away from Earth. Q1 2024, preparation for lunar approach begins, involving extensive testing and simulations of the navigation system. Mid-Q2 2024, execution of lunar orbit insertion maneuvers, a critical stage for achieving a stable orbit around the Moon. Q3-Q4 2024, final calibration and operational testing of the navigation system to ensure readiness for scientific operations. Conclusion. The Resilience mission exemplifies the meticulous planning and technological sophistication required for successful lunar exploration. The $5 million navigation system, structured around 5 distinct phases, highlights the complexities of maneuvering into lunar orbit. Each phase plays a critical role in ensuring that the spacecraft can navigate effectively and perform its intended scientific missions. The mission not only stands as a testament to human ingenuity but also paves the way for future explorations of lunar environments and beyond. The content surrounding the Resilience lunar mission's navigation system is rich with technical detail and planning, yet it also reveals some counterintuitive insights that challenge common perceptions about space missions, particularly regarding cost, complexity, and the nature of technological advancements. Here are the key counterintuitive pieces of information identified in the content. 1. Cost versus complexity. At first glance, a $5 million investment in a navigation system for a lunar mission might seem extravagant or insufficient for such a complex endeavor. However, the meticulous breakdown of this cost reveals that it is not merely an expenditure but rather a strategic investment in precision technology. The advanced navigation capabilities required to successfully maneuver into lunar orbit demand significant resources, which can lead to the assumption that high costs correlate directly with high complexity. In this case, the investment is justified by the need for accuracy and reliability, showcasing a counterintuitive relationship between perceived simplicity in execution and the underlying complexity of the technology involved. 2. Phased approach efficiency. The mission is designed around 5 distinct phases of trajectory adjustments, which might suggest a lengthy and cumbersome process. However, this phased approach actually enhances efficiency and precision. Contrary to the belief that more steps could lead to more chances for error, the structured phases allow for targeted adjustments based on real-time data. This contrasts with a more traditional view where fewer, larger adjustments are preferable, thereby highlighting that breaking complex tasks into smaller, manageable phases can lead to better outcomes in high-stakes environments like space exploration. 3. Importance of preparation over execution. Many may assume that the critical moments of a mission occur during execution, such as the lunar orbit insertion. However, the emphasis on preparation in Phase 3 Lunar Approach Preparation illustrates that the groundwork laid in advance is what ultimately ensures the success of those critical maneuvers. This counterintuitive focus on preparation underscores the idea that success in complex operations is often determined by the quality of planning and testing rather than the performance of the execution itself. For real-time data utilization, the reliance on real-time data from ground stations during the initial trajectory setup phase 1 may seem standard. But it emphasizes a counterintuitive notion that past data and models can be less reliable than live inputs during a mission. This suggests a shift in paradigm where immediacy and adaptability in navigation are prioritized over historical data, challenging traditional methodologies that rely heavily on pre-mission simulations and predictions. 5. Final testing phase as a strategic asset. The final phase, which involves calibration and operational testing Q3-Q4 2024, may appear to be an afterthought or merely a procedural step. However, this phase is critically positioned as a strategic asset. It allows the team to validate not only the navigation system but also to adjust operational parameters based on actual lunar conditions. This reveals the counterintuitive insight that the end of a mission doesn't signify completion but rather an opportunity for further refinement and learning, which is essential for future missions. 6. Technological sophistication versus human element. While advanced technology is often credited as the primary driver of mission success, the detailed breakdown indicates a significant human component in managing these technical systems. The collaboration and strategic partnerships mentioned, though not the focus of technical discussions, are essential to navigating the complexities of lunar missions. This counterintuitive view posits that human ingenuity and collaboration are as crucial as technological advancements, challenging the notion that automation and technology alone can drive success in such missions. 7. Misconception of linear progress. The timeline of events from Q1 2023 to Q4 2024 suggests a straightforward linear progression, but the reality of space missions is often nonlinear due to unforeseen challenges and adjustments. The structured phases may imply a rigid schedule, whereas the actual mission execution likely requires flexibility and adaptability in response to changing conditions. This counters the expectation that well-planned missions adhere strictly to timelines, highlighting the need for dynamic problem-solving in the face of uncertainty. In summary, the Resilience Lunar Mission's navigation system encapsulates various counterintuitive insights that challenge conventional wisdom regarding space exploration. The complexities of maneuvering into lunar orbit are not just about the technology itself but also about the strategic, human, and adaptive elements that play a crucial role in mission success. These insights offer a broader understanding of the intricacies involved in modern space missions, emphasizing the importance of preparation, real-time data, and collaboration alongside advanced technological developments. In the report detailing the Resilience Lunar Mission's navigation system, several important elements are significant yet may be overlooked by many readers. Below are key aspects that deserve closer attention, as they have implications for both the mission's success and the broader field of space exploration. 1. Investment in precision navigation technologies. While the $5 million price tag for the navigation system may seem substantial, the significance lies in the advanced technologies and methodologies being developed and utilized. Precision navigation is critical in space missions, particularly for lunar operations where gravitational influences and the need for precise timing are paramount. The investment reflects a commitment to not only achieving mission goals but also advancing the technological capabilities of lunar exploration. Significance. Investing in precision navigation systems helps to mitigate risks associated with trajectory deviations that could lead to mission failure. It underscores the increasing complexity and requirements of space missions and the necessity for advanced technology to navigate those challenges. The successful development of such systems could be leveraged in future missions, influencing broader aerospace engineering practices. 2. Phased approach to trajectory adjustments. The mission outlines a structured 5-phase approach to trajectory adjustments. Each phase builds on the previous one, incorporating real-time data and simulations to optimize the spacecraft's path. This methodical approach is essential for managing the uncertainties and complexities of space travel, especially during critical maneuvers like lunar orbit insertion. Significance. This phased methodology can serve as a model for future missions, demonstrating the importance of iterative testing and adjustments. It emphasizes that space navigation is not a one-time effort but an ongoing process that requires flexibility and responsiveness to changing conditions. Each phase allows for learning and adaptation, which is vital in high-stakes environments like space missions. 3. Importance of calibration and testing. Phase 5, which focuses on calibration and operational testing, is critical yet may be understated in discussions about mission success. This phase ensures that all systems function correctly in the lunar environment, which is markedly different from Earth. The testing of sensors and thrusters under simulated lunar conditions is crucial for validating the navigation system's efficacy. Significance. Calibration in extreme environments is a common challenge in aerospace engineering. Failure to adequately test and calibrate systems can lead to catastrophic failures. This phase highlights the importance of thorough testing protocols and the need for investment in simulation technologies that replicate extraterrestrial conditions. It also reflects the iterative nature of engineering: design, test, learn, and improve. 4. Role of ground stations and communication links. The initial trajectory setup phase emphasizes establishing communication links with ground stations. This aspect is often overlooked, yet it is foundational to the mission's success. Real-time data from ground stations is critical for accurate trajectory calculations and adjustments. Significance. The reliance on effective communication systems illustrates the interconnectedness of various mission components. Ground control plays a vital role in the real-time decision-making process during the mission. This highlights the importance of robust communication infrastructure in space missions and can inform future designs and operational protocols for both lunar and interplanetary explorations. 5. Collaborative efforts and strategic partnerships. Although some sources touch upon the strategic partnerships involved in the Resilience mission, the full scope of collaboration may not be fully appreciated. The mission likely involves various stakeholders, including governmental agencies, private companies, and academic institutions, all contributing their expertise and resources. Significance. Understanding the collaborative nature of such missions is crucial as it reflects the trend toward partnerships in space exploration. It emphasizes that no single entity can address the complexities of space missions alone. This model of collaboration can serve as a blueprint for future endeavors, fostering innovation through shared knowledge and resources. 6. Long-term implications for lunar exploration. The Resilience mission is not just a standalone project, it has implications for the future of lunar exploration and potentially for Mars missions as well. The advancements made in navigation systems, coupled with the lessons learned from the mission, will inform subsequent explorations and the development of sustainable practices for long-term human presence on the Moon. Significance. The outcomes of the Resilience mission could help set standards for future missions, influencing everything from navigation technology to operational protocols. As space agencies and private companies aim for more ambitious goals such as establishing lunar bases or conducting crewed missions to Mars, the insights gained from this mission will be invaluable. 7. Technological innovations beyond navigation. While the focus is primarily on the navigation system, the technologies developed for this mission may have applications beyond just lunar exploration. Innovations in sensor technologies, data processing, and autonomous systems could be repurposed for Earth-based applications, enhancing industries such as transportation, telecommunications, and environmental monitoring. Significance. The spillover effects of space technology development are often underestimated. The research and innovations prompted by space missions can lead to advancements in various sectors, promoting economic growth and technological progress. Recognizing these connections encourages continued investment in space exploration as a driver of broader technological advancement. Conclusion. In summary, The Resilience mission's navigation system encompasses several critical components that deserve special attention. From the importance of precision navigation and a phased approach to trajectory adjustments to the role of calibration, strategic partnerships, and long-term implications for lunar exploration, each element plays a vital role in the mission's potential success. Acknowledging these factors not only enhances our understanding of the mission but also underscores the broader impacts of space exploration on technology and society. As we continue to push the boundaries of what is possible in space, the lessons learned from Resilience will undoubtedly shape future endeavors. Here are the 4 most valuable points for in-depth analysis and discussion regarding the Resilience lunar mission's navigation system. 1. Phased approach to trajectory adjustments. The Resilience mission employs a structured phased approach to trajectory adjustments, which is critical for ensuring successful navigation to the Moon. Each of the 5 phases, initial trajectory setup, mid-course corrections, lunar approach preparation, lunar orbit insertion, and calibration and operational testing, serves a specific purpose in refining the spacecraft's path and preparing it for the complexities of lunar orbit. Discussion point. Analyze the advantages and challenges of using a phased approach compared to a more continuous navigation strategy. Consider how this approach may mitigate risks associated with gravitational perturbations and other external factors. 2. Investment in technology and precision navigation. The $5 million investment in the navigation system highlights the importance of advanced technology in modern space missions. Precision navigation is crucial for lunar missions, where even minor deviations can lead to mission failures. The sophisticated navigation system not only ensures accurate trajectory adjustments but also enhances the spacecraft's ability to respond to real-time conditions in space. Discussion point. Explore the implications of investment in navigation technology for future lunar and deep space missions. How does the financial commitment to advanced systems like Resilience's navigation influence the overall success and safety of such missions? 3. Importance of calibration and testing. The final phase of the Resilience mission focuses on calibration and operational testing of the navigation system in the lunar environment. This phase is essential for verifying that all sensors and thrusters function correctly under the unique conditions of the Moon, which can differ significantly from conditions experienced during Earth-based testing. Discussion point. Consider the critical role of calibration and testing in the context of space exploration. What methodologies can be employed to ensure that systems are adequately tested before and after lunar orbit insertion? How can these practices be standardized across different missions? 4. Strategic collaborations and partnerships. While the technical specifications of the navigation system are significant, the mission's success also relies heavily on strategic partnerships and collaborative efforts. Collaborations between different organizations can lead to innovations in technology and shared expertise, which is crucial for addressing the complexities of lunar exploration. Discussion point. Evaluate the impact of strategic partnerships on the development and implementation of navigation systems in space missions. What best practices can be derived from the Resilience mission that could benefit future collaborative efforts in exploration? These points provide a framework for discussing the complexities and technological advancements involved in lunar navigation systems, emphasizing the importance of strategic planning, investment, and collaboration in achieving mission success. 1. Apollo 11 Mission 1969. The Apollo 11 mission is perhaps the most famous lunar mission, marking the first successful manned moon landing. NASA's navigation system for Apollo 11 involved intricate trajectory calculations and mid-course corrections to ensure a precise approach to the Moon. The mission included a series of maneuvers such as the Translunar Injection (TLI) and Lunar Orbit Insertion (LOI), where the spacecraft's engines fired at specific times to adjust its trajectory. Just like the Resilience mission, Apollo 11 relied heavily on real-time data and precise navigation to achieve its historic goal of landing astronauts on the lunar surface. 2. Lunar Orbiter Program 1966 to 1967. This was a series of 5 robotic missions launched by NASA to map the Moon's surface before the Apollo program. The Lunar Orbiter spacecraft utilized a detailed navigation system for trajectory adjustments and lunar orbit insertion. Each orbiter had to perform mid-course corrections to ensure it reached the intended orbit around the Moon for optimal imaging. The success of the Lunar Orbiter missions laid the groundwork for subsequent Apollo missions. Much like how the Resilience mission builds on past lunar exploration to enhance navigation technologies. 3. Chang'e 5 Mission 2020. China's Chang'e 5 mission aimed to return lunar samples to Earth. It featured a complex navigation system that involved multiple trajectory adjustments and precise calibration of thrusters throughout its journey. The mission included phases for lunar orbit insertion and sample collection similar to the 5 phases outlined for Resilience. Chang'e 5 successfully executed its maneuvers, demonstrating advanced navigation capabilities that are reflective of the technical sophistication aimed for in the Resilience mission. Future outlook, predictions for lunar navigation systems post-Resilience. As we look ahead beyond the Resilience mission, which is set to conclude its navigation system operations by late 2024, several predictions can be made regarding the future of lunar navigation systems and their implications for space exploration. The advancements and lessons learned from Resilience's $5 million navigation system will likely influence various aspects of lunar missions and beyond. 1. Enhanced autonomy in navigation systems. One significant trend expected in the future of lunar navigation is the increased autonomy of spacecraft. The success of the Resilience mission's phased trajectory adjustments will pave the way for more sophisticated onboard decision-making algorithms. Future missions will likely employ advanced artificial intelligence and machine learning techniques that enable spacecraft to autonomously adjust their trajectories in real time, reducing the reliance on ground control. This autonomy will not only enhance the efficiency of navigation but also improve the response time to unforeseen challenges during missions. 2. Integration of advanced sensor technologies. The Resilience navigation system emphasizes the importance of precise thruster calibration and sensor accuracy. Future lunar missions will likely see the integration of even more advanced sensor technologies such as LiDAR and improved star trackers. These sensors will provide enhanced spatial awareness and real-time environmental mapping, allowing for safer landings and navigational adjustments. The ability to assess the lunar environment in real time will be crucial for missions aiming to establish permanent bases or conduct extensive exploration. 3. Collaboration across international space agencies. The Resilience mission illustrates the potential for collaboration between various space agencies and private sectors. Moving forward, we can expect more international partnerships for lunar missions. These collaborations will facilitate the sharing of technology data and best practices, leading to more robust navigation systems. Joint missions could capitalize on collective expertise, enhancing mission success rates and fostering a spirit of cooperation in space exploration. 4. Development of lunar infrastructure. As lunar missions become more frequent, the establishment of lunar infrastructure will be essential. Navigation systems will evolve to support not only crewed missions but also the operation of lunar bases and habitats. Future navigation technologies will need to account for the complexities of navigating between various lunar facilities and conducting supply missions. Infrastructure development will require adaptive navigation solutions capable of managing multiple operational scenarios, including communication delays when relying on Earth-based control. 5. Application of navigation technologies to Mars and beyond. The lessons learned from lunar navigation systems will likely have profound implications for future Mars missions and beyond. As space agencies prepare for human exploration of Mars, the experience gained from the Resilience mission will inform the development of navigation systems for interplanetary travel. Technologies that prove successful in lunar navigation, such as advanced trajectory planning and autonomous operation, will be adapted for missions to more distant destinations. 6. Increased focus on sustainability and safety. As space exploration continues to expand, the focus on sustainability and safety will become paramount. Future navigation systems will be designed with fail-safe mechanisms and redundancies to ensure the safety of both crewed and uncrewed missions. This focus will include not only the technical aspects of navigation but also environmental considerations such as minimizing the impact on the lunar surface and ensuring the safe operation of multiple spacecraft in orbit. 7. Real-time data sharing and cloud-based navigation systems. The future of navigation systems may include a shift towards cloud-based data sharing platforms. By utilizing real-time data from various sources, including satellites and ground stations, navigation systems can enhance their accuracy and reliability. Future lunar missions may incorporate real-time data analytics, allowing for dynamic trajectory adjustments based on the latest information regarding lunar conditions, gravitational influences, and space weather. Conclusion. The Resilience mission's navigation system represents a significant step forward in lunar exploration. As we project into the future, the implications of its advanced technologies and methodologies will be felt across multiple dimensions of space exploration. The integration of autonomous systems, advanced sensors, international collaboration, and adaptive technologies will redefine not only lunar navigation but also pave the way for humanity's next steps in exploring the solar system and beyond. As we prepare for a new era of exploration, the groundwork laid by missions like Resilience will be instrumental in achieving ambitious goals in space exploration.